Now, in the last video, we have seen what is the flux. Now, to continue with it, if the electric field is uniform, the electric flux passing through a surface of vector area A is phi E is equal to E dot A, where both E and A and even phi E are all vectors, and EA cos theta. It will give, this is a dot product, it will give me EA cos theta. Now E is the magnitude of electric field, A is the area of the surface, and theta is the angle between the electric field lines and the normal perpendicular to A. The area vector of a surface denoted by A points in a direction perpendicular to the surface and has a magnitude equal to the area of the surface. If the surface is closed, like that means if it is a bangle like surface, then it divides the universe into inside and outside. Then by convention area vector points outward. So it is very essential in electrostatics to understand whether your surface is closed or not. Consider again a bangle, and if it is broken, then it will not be a closed surface, it will be an open surface. Then if your electric field is non-uniform, then electric flux is d phi E. It's a differential one, differential flux through a small surface area dA, and it is given by d phi E is equal to E dot dA. Again, E is electric field, but multiplied by the component of area perpendicular to the field. And dA is the vector representing an infinitesimal element of area surface. So this slide will make it more clearer. This is my electric field going this way, and there is a virtual surface here. Now see, this is my electric field direction and this is my area vector direction, and this is the angle between the two. This is my theta. So phi E is EA cos theta, where E is now magnitude of electric field, A is magnitude of area vector, and cos theta is the cosine of angle between the two. Now if I make this vertical like this, then area vector will be like this, and the angle between the two will be 0. Eventually cos theta will be equal to 1, and the maximum flux will pass through the surface, or this virtual surface, I mean to say. Then if this bend like this, and if it becomes perpendicular parallel to electric field, then the angle between the two, that is area vector, will be now like this. Means the surface is like this and area vector is like this. So angle between the two will be 90. So cos theta will be 0. Means the field will be 0. The flux through the surface will be 0, or it will be minimum. It is very important in electrostatics to understand the type of the boundary. In this particular image, you will see the charge is enclosed, and this is the boundary, and this is closed. So there will be a net flux flowing out of the surface. As opposed to this, if you see this area, then this is a charge, but it is not enclosed by the boundary or the surface. It is an open surface. Therefore, the flux through this will be 0. Means there will not, this is not applicable itself. We can't consider these type of surfaces. We have to consider only these surfaces. Now we talk little bit more about area vector. Area vector is normal to the flat surface and can point in either direction from the surface. Means the area vector can be like this also and like this also. This is a flat surface like a paper sheet. Now you can choose this area vector here and the normal here, or it can be like this. But if you choose the area vector this side and the normal vector here on this side, then it doesn't become consistent and it is not allowed. Here we will consider some examples. This is a open surface. This is slightly curved. Area vector or the normal can be drawn here or here. But if I am drawing a normal here, then this will be the direction of area vector. If I consider this particular surface element here next time, then also the area vector should be like this. For closed surfaces, you need to have area vectors in this direction, outward direction only. The inward direction is not possible. So just look at these three cases. This is the open surface. S1, area vector can be here, area vector can be here. Here, so this is not allowed. Either it should be here or it should be here. Here again the two area vectors are pointing out and this is inside opposite direction. So again this is not allowed. Whereas this and this, all the three are in same direction. So this case is allowed. So this is what you have to remember when you solve the problems. Look at this, remember this, remember this. These pictures I've taken from this website and the due credit is given to them. Now we have some smooth surface, but it's not flat, it's curved like a ribbon. So what has been done is these three small things, this entire thing is cut into patches, and a very tiny patch will be like a flat surface only, and then we have this E vector and this N vector. This is a trick. But again remember, all this N will be pointing in the same direction. No N will be going in the other direction. So now, finally, what is the Gauss's law? With so much of discussion with the flux, Gauss law says the total flux linked with a closed surface is 1 upon epsilon 0 times the charge enclosed by the surface. So this enclosed word is very important. So you have integration over closed surface E dot dA or E dot A is equal to 1 upon epsilon 0 Q enclosed. For example, if Q is the charge placed inside a cubic cube of HA, then as per the Gauss law, simple, you get immediately the net flux through each surface of the Q is Q upon 6 epsilon 0. Electric field of a surface is calculated by Coulomb's law also. We can very easily use Coulomb's law. But to calculate the electric field distribution in a closed surface, we need to understand the concept of Gauss's law. In fact, I will say Gauss's law is only a restatement of Coulomb's law. It is said in a different way. If we apply Gauss law to a point charge enclosed by a sphere, we will get back the Coulomb's law easily. Now, let us understand how electric flux is related to Gauss law. When we talk about the relationship between electric flux and Gauss law, it states that the net electric flux in a closed surface will be zero if the volume that is defined by the surface contains a net charge. So to establish the relation, we will first take a look at the Gauss law. Gauss law is simply written as, without using any integration, phi E is equal to Q upon epsilon 0, where epsilon 0 is electric constant, which I mentioned, 1 upon 4 pi epsilon 0 or 1 upon epsilon 0 being the constant quantities, we will call it as electric constant. Epsilon 0 is permittivity of free space. The electric flux phi E can be defined as surface integral of the electric field, and it is given as phi E is equal to integration over surface. These two means phi E is equal to E dot dA, or I can write down Q is equal to integration E dot dA. So in that sense, you can very easily see phi E and Q are same. Only thing is you have to divide Q by epsilon 0. So once I get Q, it's not very difficult to estimate what is electric field. So the flux is considered as an integral of the electric field. The relationship which is shown here is called as integral form of Gauss's law. As per the Gauss law, the total charge enclosed in a closed surface is proportional to the total flux enclosed by the surface. Therefore, if phi is the total flux or phi e is the total flux, epsilon 0 is electric constant, then I can write Q is equal to phi e epsilon 0, or Gauss's law formula can be expressed simply without having any integration. Phi e is equal to Q upon epsilon 0. Now, this slide is very, very important. This again is taken by this particular website. So I am giving them the due credit, this slide credit. See, this is a cube. There is a charge enclosed here. This is a surface. The field lines or the field lines flux is coming outside. This is called as outward flux. Now, these are the two charges, positive charges. The flux is coming outside. Now this is one negative charge, the flux is going inside. There are two negative charges, the flux is also going inside. Now the question is, if I have one positive charge and one negative charge, what should be done? This can be a good problem. We will solve these type of problems later on. This positive charge is called as sources and these negative charges are called as sink for the electric field. Now, changing magnetic field, which creates electric field, cannot act as sources or sinks of electric fields. It has to be this isolated charge Q. How now Gauss's law is related to Coulomb's law? One of our fundamental relationship between the two laws is that Gauss law can be used to derive Coulomb's law or vice versa. Consider a point charge Q. If we apply Coulomb's law, the electric field generated is given by E is equal to K into Q by R squared, where K is electric constant. Now, take Gauss's law. If we have a sphere of radius R that is centered on a charge Q, now for the surface S of the sphere, we will have integration over surface E dot ds, which I sometimes refer to A also. It will be, I'm just having this equation kq upon r square ds. This k, q and r square are constant. So integration over ds. So if I integrate over the sphere, it is going to be 4 pi r squared. And substituting, I get the Gauss's law back. At the end of this equation, we can see that this resembles to Gauss's law. So that is the reason I always say Gauss's law is a restatement of Coulomb's law.